Hello, friends. Excited to spend a little bit of time with you here today. Let's go ahead and share the screen and let's get started. All right. Um, so what I wanted to look at today was this exam 6, which comes from chapter 7. And it says, write a program to demonstrate the number of people needed to ensure that the probability of at least two of them have the same day of the year as their birthday is at least 70%, 80%, 90, 95, and 99%. Okay, so let's go ahead and let's get this program started. It says, hint, use example 13 from 7.2. All right, getting the clip started here. Splash screen is opening up on a different screen. I will admit I'm using a computer I don't normally use. It should be my daily driver, but she's got such a beastly power supply that she usually cooks me out of the room. But anyway, it's been a while since I've opened it up Eclipse, and she's letting me know that she doesn't appreciate that. So, all right. So just to make sure that I can pulling everything down from, they used to call it the master branch. Now we call it the main branch. Anyway, it's been a while since I've done that. And so I wanted to make sure that we got in here and started off just with a clean branch. Well, that's opening up. I've got the student resources folder here pulled down. Let's go in and let's see if we can find that example that it's referring to. Okay, so in the textbook, it says 7.2 example 13. Is this it? Yeah. And we'll change the view. Okay. Here we go. Example 13. A famous puzzle asks for the smallest number of people needed in a room, so it's more likely than not to have at least two of them have the same birthday. Most people find the answer, which was determined to be surprisingly small. After we solve this problem, we'll show how similar reasoning can be adopted. Okay. So what's the minimum number of people needed to be in a room so the probability of two of them have the same birthday is greater than a half? All right, so let's come in here. What's this say? All right, well, I think that might just be, we'll have to be okay with that. Let's see, file, import, because this one doesn't have discrete structures in it. Existing projects. Yeah, that's the one we need. So I'll go ahead and click finish. And now there we can see discrete structures. Got exam. And so this is going to be new package, and I'm going to call this all right. People in a room for a birthday. So I'll go ahead, public static void main, and let's just get this started. So does it run? It does. Happy to see that. Okay. So we'll say we'll just start out and try to work through the example. Okay. Furthermore, we assume birthday of the people are independent. Okay. Equally likely 366 days per year. Okay, so let's go in and fix that in our code. Okay, more people are born on some days of the year than others, such as days 9 months after holidays. Fun family fact, right? I mean, things you don't expect to see in a discrete structures book. All right, define the probability of 2 of n people in a room have the same birthday. We calculate probability n have that these people all have different birthdays. Then the probability that at least 2 people have the same birthday is 1 minus p of n. To compute p of n, we consider the birthdays of n people in some fixed order. So let's come in here and let's say int number of people. And I'm going to start out with 2 because you have to have as a minimum 2 people. Okay. Imagine them entering a room one at a time. We'll compute the probability that each successive person entering the room has a birthday different than those people already in the room. Okay. The birthday of the first person certainly does not match that one of anybody in the room. So we can come back in here and I'll say all right, the probability that the second person in the room is different than the first is 365. So we'll say double probability of second equals, fix this just a little bit. I'm trying to make some notes as I go, right? So this is going to be I'm recasting these as double so I don't get a rounding error. Yeah. All right, let's just print this right quick. And just because I'm looking for a pattern here. I'll make sure, yeah, it's less than 1. So that's what I was hoping to see. Okay. The assumption is that it is equally likely for someone to be born on any of the 366 days per year. In theory, if we assume they're all equally likely. Now, the third person is going to be 364. So we come in here. And this one should be a slightly, oops, smaller number, right? Okay, yeah, so 997 versus 994, slightly smaller number. Okay, in general, the probability the jth person is as follows. So, has a birthday different from the birthdays of the previous j minus 1 people already in the room, given that these j minus 1 people have different birthdays, is 367 minus j over 366. So that's just a little bit of simplification there. So 366 minus j minus 1, that becomes 366. The minus times a minus becomes a positive, so 366 plus 1 minus j, or 367 minus j. Because we have assumed these birthdays are independent, we can conclude the probability that n people in the room have different birthdays is this. So it follows that the probability among n people that there are at least 2 people with the same birthday is as follows. To determine the minimum number of people in the room so that the probability of 2 of them has the same birthday is greater than half, we use the formula we have found for this, which is as follows. To compute it for increasing values of n until it becomes greater than 1/2. Okay, so this is the basic formula. Okay, so we need to do n. All right. Let's come in here and we'll say while, let's do while 1. What do they give for an answer? So after considerable computation, we found n equals 22 is 475 and 23 is 506. Okay, so this shouldn't be too bad. So we're going to calculate. So it's 365 times 364 times, so it's, we'll do while true, and then we'll say I'll start out here. So I'll say let's do this. We'll say it'll be fine. We'll do it in here. Int, no, double odds of 2 with the same way equals 0. I really haven't quite figured out how to get this. Oh, I see what I was supposed to do. I was supposed to multiply these up here. So let's do this. So those are long odds. And what's the books they were supposed to do? okay, so in general, the probability that the jth person has a different birthday from the birthdays of the previous people in the room is this. Okay, so because we've assumed they're all independent, we conclude that the probability that n people in the room have different birthdays is this. So it's a sequence. We have assumed we can conclude the probability that n people in the room have different birthdays is this. So the odds that they're going to have a different birthday is going to be the 365 times the 364. Okay. And this is going to be multiply this number times this number. Okay, almost a sure thing that it's not going to have two people. Okay. So let's do this. For int people count equals 2. I'm gonna trim that down just a little bit. Let's make it 10. Let's see what that looks like. Okay, people count. Get that tidied up just a little bit. Okay. All right, so that's not too terribly bad, right? Now we just need to find the probability. So each time we have our initial term. So this is our initial term, so I'll do that. Initial term equals, and that's going to be 365 divided by 366. Is that right? And then the second one is going to be, so probability that the third person is 364. Oh, I see. Right, because that's the odds that the first person, okay, and so when people count equals 2, it's going, okay, so we're going to do okay. I'm going to do People count. No. Days per year minus people count. And I need to recast these as doubles. It's just a semicolon. Okay. Okay. All right. So let's just see what that generates for numbers. Cool. So we're getting up to 11%. They said like 23 people got it done. Yeah, here we go. So 22, 23 does 21, 22. Let me see if that matches the book or if I've got an off by one error. .506. So 475 and 506. Let me see if I've got. Okay. So I think I've got an off by one error. And this is not an elegant way to do that. Well, it's going to be something in that range, and I'm not going to feel terribly bad about that. So 22 and 23, right? So 22, it's 475. I get 475, and 23, they get 506. All right, so yeah, a couple off by one errors. They're in the loop, but not too bad. Okay. So let's go ahead and let's make this up to 40 and see if that gets us to the 99. Nope. 50, 97, 60, 99. There we go. So 59 is not quite there. Well, no. It looks like, for my money, I would call 55 people in the room as the right number of people in the room, because that's going to round up to 0.99. Let's revisit the question right quick. Write a program to demonstrate The number of people needed to ensure the probability of at least 2 of them in the room have the same birthday of the year is at least 70%, 80, 99%. Okay. All right, so this is a program that demonstrates the number of people needed in the room to ensure those different numbers. All right, so what I'm going to do is I'm going to stop the program there because that does do the calculation for us. And all right, and I'll stop my share. So anyway, I look forward to seeing everybody's solutions. Thank you all for your time. Have a wonderful day.